Hi everyone, welcome to our week 6 of Graduate Statistics, University of Cincinnati. We have just, last week we focused on providing you with an introduction to inferential statistics. So we did that through simulations, the idea being that when you're making inferences about what you see, the patterns that you see in your data, you want to make sure that you can compute the likelihood of observing that data under random conditions. Because that probability is what will drive the inference. If the probability of seeing a particular result, say a particular difference in means, a particular correlation, is very low under random conditions, then we start thinking that something might be going on that's driving those patterns in our data. But if the probability of seeing a particular pattern in our data is likely under random conditions, then we begin to think that maybe nothing is going on. It's just a matter of sampling error. And we played around with that gender bias data from the 1976, where an observation was made that there was a 30% difference in promotion decisions between males and females. And we wanted to know if that difference is likely to be observed under random conditions. So we kind of created a random experiment that we performed physically with cards, and then I showed you how to go on and do that experiment through simulations because it's much more effective. And we constructed from the data that we obtained from the simulated experiment a probability distribution, a distribution of the data that allowed us to compute the probabilities of observing the particular finding that we observed, which was a 30% difference, right? So this is how the inferential process works in statistics, and it's because we observed that there is very low likelihood that a difference of 30% in decisions would happen just by chance that we dismissed the null hypothesis in favor of the alternative hypothesis. Now, I want to get into that concept of probability distributions in general. Most of the times when you do data analysis, you do not run random experiments because we can count on probability distributions. And a very famous one is the normal distribution, which is going to be the focus of this class. And we will learn how to use the normal distribution to put data in context in order to make appropriate recommendations and appropriate decisions because we're not looking at the raw data and perhaps being tricked by patterns that occur when things are not normalized. So that's one goal. The other goal of this class and the lab will be to get you started practicing communicating the findings of your analysis. This will be an important component of this course because I want you to practice presenting and talking about data. It doesn't matter if you're going to be a data analyst or not. If you're going to be a person that will make informed decisions based on data that perhaps somebody else conducted and analyzed, it's important that you're able to communicate those ideas to others around you that will be your support system to accomplish whatever it is that you want to do. So let's move on. Let's get started. Probability distributions, and again, the focus will be on the normal distribution, but there are many others that we'll encounter during this course as we learn to do specific statistical tests. So let's start with an example. How good is this SAT score? So imagine that a college admissions officer received an application of a student whose SAT score was 1800. Imagine the officer was somebody like me that has no historical experience with this exam to determine what is typically a good score. It may be the case of some of you that are not from the United States. We have no idea what does a score of 1800 even means, right? So we need to put things in context. And the question is, what information would we need, or the officer need, to make an informed inference about how well ranked the applicant is based on the SAT score. Think about it for a second. What would be the information that the officer would need? If you're thinking that it would be useful to know, let's say, what's the mean score that everybody gets, take everybody that always takes the test, like the population of test takers. What's the average score that people get? And that would be true, right? You can compare that score with respect to the mean. If it's above the mean, that's a good thing. If it's below the mean, not so good. But then it's nice to also have the spread of the data, because then we can have more than this gross assessment of simply above or below the mean, but we can start thinking, okay, but how much above the mean? Not in raw terms, not just by subtracting the raw score from the mean score, but in terms of how many standard deviations above the mean is that score. And third, to do those computations, we need to know the shape of the distribution in order to figure this out. So with these three informations in hand, even somebody that has no historical context with this data, with SAT scores, can actually interpret the result of the test. Let's see how. So again, just to restate, we need these three things about the population of all test takers so that we can look at this one test taker that we're interested in and see how they perform with respect to that full population. So the normal distribution is the one that we use very frequently in statistics, because there is a lot of variables that are distributed like that, right? That are distributed this way. You have common scores in the middle that become less and less frequent when they go to the extreme, to one side and the other. That distribution shows up with a lot of variables in the real world. And what's the characteristic of that curve? It is unimodal and symmetric. It's like a bell curve. Follows very strict guidelines about how variably the data are distributed around the mean. And if that's kind of obscure right now, you'll see what I mean in a bit. And many variables are nearly normal, but none are exactly normal, but good enough. So it's an idealized distribution of the data, because we're not running the actual random experiment. You have an idealized distribution of what you can expect in terms of scores in the general population. And that distribution has a mean and has a standard deviation. So if you have the mean of the population, in this case, the mean SAT score in the population, the standard deviation of SAT scores in the population, note that I'm using mu and sigma because I'm talking about parameters in the population. So I'm not using X and S to represent mean and standard deviation in the sample. And I'm saying that if you have that and you know that the distribution is normal, you can actually figure out how good that score is. Let's see how. First, I just told you that the normal distribution follows very strict guidelines about how variably the data are distributed around the mean. And here's what I mean. For a normal distribution, there is this thing called the 68, 95, 99.7 rule. And that rule says the following. 68% of the data is expected to fall between the mean minus 1 standard deviation and the mean plus 1 standard deviation. About 95% of the data is expected to fall between mean minus 2 standard deviations and mean plus 2 standard deviations. And finally, virtually all of the data is expected to fall between mean minus 3 standard deviations and mean plus 3 standard deviations. So given that we know these things, it helps us know the likelihood that a particular score has, right? And how the score is located with respect to the mean. So let's check first our understanding of this rule, and then we'll get back to the problem, I promise. Imagine a doctor collects a large set of heart rate measurements that approximately follow a normal distribution. He only reports 3 statistics to you. The mean, 110 beats per minute, the minimum, 65 beats per minute, and the maximum, 155 beats per minute. Which of the following is most likely to be the standard deviation of the distribution? Here are your options. Pause the video and try to work this out. Come back when you're ready for the explanation. So here we go. The normal distribution is here. It's always useful to draw things. Let me get myself out of the way. Here's the mean. And we're saying that, the doctor gave us the distribution. It's normal. Gave us the mean, which is the center of the distribution. And he gave us the range of the distribution, 65 and 155. We're going to apply the 68, 95, 99.7 rule to figure this exercise out. The idea being that pretty much 100% of the distribution should fall between the mean plus 3 standard deviations and the mean minus 3 standard deviations. So if we go, alternative by alternative and figure what the values for mean plus 3 standard deviations would be, we can perhaps get to the answer. So let's try it out. In this first one, let's consider if the standard deviation were 5. Let's look at this. Mean plus or minus 3 times 5. 3 standard deviations means 3 times 5 in this case. We would have 15 plus 110, it would be 125. 15 minus 110 would be 95. That's out here. That's not expected in a normal distribution, right? So not this one. Now let's try the next. In this case, if I substitute standard deviation by 15, I see that 65 and 155 pretty much grabs all of the data, which is the expectation in a normal distribution, right? Close to that, close to 100%. So this would be the right alternative. Note that if I tried 35, that's way out. So you would go from 5 to 215. That would not be the expectation if you have a normal distribution. Normal distribution, again, 100% of the data, more or less, should fall between the mean plus or minus 3 standard deviations. So if I replace the standard deviation with 15, that gives me the range of the data. That indicates the range that includes 100% of the data. So that's why this looks like the correct answer. And alternative D, again, would make it way much broader than would be expected of a normal distribution. Oh, Paula, but what if there was like a 64 to 156? Yeah, then the question would be ambiguous. If we had other standard deviations that would give us something that's kind of close to this, a bit broader, then it could be the correct answer. Because as we said, not 100% will be between, not 100% of the data will be between mean minus 3 standard deviations and mean plus 3 standard deviations, but almost 99.7. So in this situation here, this would definitely be the closest approximation to the standard deviation. We'll come back with the next video where we're going to now start using our understanding of the normal distribution to solve our problem. The problem we'll begin with about the SAT. See you soon. Bye.